Good morning, student. Good morning to all of you. Today we are going to discuss a topic that is magnetic field due to infinitely long cylindrical wire carrying current on its surface. B equal to what? Inside and outside of the wire. Okay. Let us see here. Suppose this one a cylindrical wire. Okay. Suppose this one a cylindrical wire having a length that is infinite. Okay. Suppose this one cylindrical wire and the current which is flowing which is on the surface of the cylindrical wire. In the heading, magnetic field due to infinitely long cylindrical wire carrying current on its surface, that is the current which is flowing which is on the surface of that cylindrical wire. Okay, the current is only on the surface. Means what? Suppose this one a cylindrical wire. Okay, this one cylindrical wire, and the current which is passing only on the surface of the cylindrical wire. The current is not available inside of the wire, that is in inner portion of the wire, whereas the current is only available on the surface of the, that is current is going upward direction only on the surface of the cylindrical wire. Okay, so and the wire is infinitely long. Okay, here the wire is infinitely long. Okay, the radius of this wire is, suppose we call as capital R. Okay, and we have to find out the magnetic field which is inside of the wire, that is suppose this one axis of the wire, suppose this one axis of the wire, and you have to find out the magnetic field at a point P, that is the point P at a distance r from the axis, and again the magnetic field, this one the inside of the wire and outside of the wire, means we have to find out the magnetic field which is outside of the wire. Suppose this a point Q. Okay, and this distance is r, that is the r is variable here. Okay, here r is variable, here r is variable, means at a distance r at a point Q which is outside of the wire, we have to find out the magnetic field at a point P which is inside of the wire, and we have to find out the magnetic field at a point Q which is outside of the wire. Only the current is available on the surface of the wire only. Okay, so here we are going to use the Ampere's circuital law to find the magnetic field at a point P and Q. Okay, what is Ampere's circuital law? We know that Ampere's circuital law, according to Ampere's circuital law, the integration of B dot dl is equal to mu naught and the current which is inside of the loop. We assume a loop and the current which is present inside the loop, the current we will consider here. This one the formula of Ampere's circuital law. Okay, so we take the top view of the wire. Okay, we take the top view of the wire. So the wire is like that. This one the top view of the wire, and the current is outward, means upward. The current is here upward. As you take the top view of the wire, here the current is going outward of the board. So we represent as a dot. Okay, means the current is going outward. Okay, the current is going outward. Okay, and we have to choose. We have to draw a circuital loop, that is Ampere's loop, where you find out the magnetic field. This one, the center of the loop. Okay, and we have to find out at a point P at a distance r. Then we have to draw a loop which is crossing to that point. We have to draw a loop so that it crossing that point where you want to find the magnetic field. This loop is called Ampere's loop. This loop is called Ampere's loop. and we have to consider that current, that is the I inside means what, the current which is present inside of the loop. Here if you apply the formula, that is B dot dl equal to mu naught I inside. Here we see what is the amount of current which is present in the loop. There is no current which is present in that loop. Here I is equal to 0. Inside of the loop there is no current. All the current is only on the surface of the wire. So the current is outside of the loop, not inside. So here the current is 0. So here the B dot dl equal to 0, and we call as the B equal to 0. Here the magnetic field which is inside of the inner point, that is inside of the wire, is 0 at a distance r. Okay. What about the magnetic field at the outside of the loop? Here the r, that is small r, is less than capital R, the radius of the wire. That is here the r is less than capital R. If r is less than r, then the magnetic field will be 0. That is inside of the loop. Okay, that is inside of wire. That is inside of wire. But what about the outside of the wire? Outside of wire. Outside of wire means here the small r is greater than capital R. Here the small r, that is the small r which is that distance at a distance point q, the small r is greater than the radius of the wire. So again we have to draw the top view of the wire. Here suppose this one, the top view of the wire, and the current is coming outside. So we represent as a dot. Okay, and we have to find out the magnetic field at a distance r, at a point q. At a point q, we have to draw a loop, that is Ampere's loop, where you want to find the magnetic field. There you have to draw the Ampere's loop. Here we want to find the magnetic field at a point q, so we draw a loop which is crossing the point q. This loop is called Ampere's loop. This loop is called Ampere's loop, and on that loop we have to find out the magnetic field. We have to find the magnetic field at a point q. Okay. There if you consider the current is going outside, then according to right hand thumb rule, we put our thumb in the direction of current and our 4 curling fingers will give the direction of magnetic field. So here the magnetic field will be tangentially. We assume that the magnetic field here at tangentially. Okay, we consider the magnetic field as tangential, and we have to cut the small distance dl on that loop. This dl direction, the direction of this dl is also in the direction of b, because we consider the direction of loop is in the direction of b. So this one the direction of loop. Okay, so the direction of dl is in the direction of loop. Okay, so there is this one, the dl having direction is in the direction of b. Okay, so what about the angle between the b and d? Here the angle between b and d becomes 0, that is theta equal to 0 here, because the b and the dl both are in same direction, so the theta becomes 0. Why we consider the dl is in the direction of b? Because we consider the direction of loop is in the direction of b. Our choice, we can consider any direction in the direction of loop. So we consider the direction of loop is anti-clockwise, and we see that the b is also in the anti-clockwise. So the direction of dl is in the direction of loop. So here the dl is in the direction of b and the theta becomes 0. After applying the rule of Ampere's circuital law, we see that b dot dl equal to mu naught I inside. Here b dl cos 0, because theta is 0, and mu naught, and the current which is inside of the loop, I inside means the current which is inside the loop. Here the loop is outside of that wire, so the all the current present inside the loop. So we know that the amount of current is I here. So we put here I, okay, and here the B will be come out because the B is constant, and integration of dl cos 0 1 equal to mu naught into I, and as you integrate the dl, length of dl, we get the circumference of this circle, that is 2 pi r, B into 2 pi, and the radius, that is r. We consider that the radius r, the distance r means the radius becomes r, 2 pi r equal to mu naught into I, and from here we get the value of B, that is mu naught upon 2 pi I upon r. We see that what is the magnitude of magnetic field at the outside of the loop. Here we see that the hollow wire behaves like a single wire. The hollow wire, the current which is present on the surface of the wire behaves like a single wire which is passing through the center of the wire, because this one, the value that we have find in the previous lecture, this value, that the magnitude of magnetic field due to a single current carrying wire, infinite current carrying wire. I think you were able to follow me. Thank you very much.